Hello and welcome everyone. This is the final or third episode of chapter 22. Our next application will be pulse width modulation using an analog to digital converter.
Before we get into the practical part, let's clarify what pulse width modulation, or PWM for short, is. You might have heard more about this in the 15th and 17th chapters of the curriculum, but for now, I'll summarize the most important terms. A pulse width modulated signal is a square wave signal whose duty factor can be modified. This means that the square wave signal is high for some time, say t on, and low for some time, marked t off. The sum of the two times gives the period of the square wave, which is marked with a capital T. Thus, this large T equals t on plus t off. Then, the ratio of t on to the period t gives the duty factor of the rectangular signal, which is usually marked by a small delta. This value can vary between 0 and 1, or in percentage terms, between 0 and 100%. The power of a rectangular signal is proportional to the area of the geometric shape bounded by the horizontal axis. So the smaller the duty factor, the lower the power of the signal, and vice versa. The larger the duty factor, the higher the power. Therefore, by driving a light-emitting diode with such a pulse width modulated signal, we can adjust the brightness of the LED. We will explore this in today's practice circuit. Let's assemble the circuit shown in the figure. It can be seen that the high byte of the AD value of the potentiometer on the PA1 pin, which corresponds to ADC channel 1, is written into the PWM register of TMR2, i.e. the potentiometer is used to adjust the duty cycle of the PWM signal appearing on PD7 pin. And then, this signal will drive the light-emitting diode connected to PD7 pin. When you have assembled the circuit, you can check if your circuit diagram is correct by using the photo in the curriculum. When the circuit is done, we can start the software development. First, we initialize the input-output ports. To initialize these input and output pins, see function ioinit in io.c file. On port A, port B, port C, port D, we turn off the pull-up resistors and configure these pins as inputs, except the PA0 pin on port A, because this controls the status LED. Another exception on port D is the PD7 pin, which is a special function. According to chapter 12.3.4 of the datasheet, the PWM output of timer 2 is on this pin. The next step is to initialize the clock. The clock is initialized in timer.c using the timer init function. The bits of the TCCR1B register are described in chapter 16.11.2 of the datasheet. Here, table 16.6 shows that if no prescaler is needed, then bits CS12, CS11, CS10 must be set 0, 1, 1 in this order. We do not set the value of the remaining bits, as we do not need them, so their value remains the default 0. Furthermore, as described in chapter 16.11.7, enable the interrupt of timer 1 by setting the TOIE1 bit and finally enable the interrupt, the global interrupt. Next, the pulse width modulation is set. The setting of the PWM can be done with the PWM init function of the pwm.c file. Here the setting of the TCCR2 register has to be done. For timer 2, we don't use clock division in accordance with timer 1, so a prescaler is not needed, as it can be seen in chapter 17.11.1 of the datasheet. According to the datasheet table 17.2, when selecting operating mode 1, the output waveform will be phase correct. WGM21 is set to 1, WGM20 is set to 0. The behavior of COM20 and COM21 pins depends on the selected operating mode. In mode 1, the table 17.5 is valid, which in non-inverting operation, setting COM21 and COM20 pins to 1 and 0. Then, the ADC must be initialized, so the AD conversion must be started. To initialize the ADC, we must first set the ADC reference voltage in the ADC init function using the ADM-UX register according to chapter 22.9.1, which in our case, as in the previous example, equals the external analog AVCC voltage. To do this, set REFS1 to 0 and REFS0 to 1. Using table 22.4, we select the register bits to set so that the first channel, which is ADC1, is the input. For this, MUX0 must be set to 1, the remaining MUX bits can remain at the default value of 0, and they do not need to be set. If the ADLR bit is 1, the result is left-aligned in ADCRH. It means that the result is displayed on the top 8 bits. See measurement example 1 for an explanation in the previous video. After initializing the ADC, you can enable the ADC with the ADC enable function. In the ADCSRA ADC controller register, we can set the clock rate of the ADC relative to the clock. We set this prescaler to 128 based on chapter 22.9.2 of the datasheet. Enable interrupt and the operation of the ADC. In the beginning, the duty cycle of the PWM is 0, that is, the LED connected to PD7 should not be lit. This is achieved by setting the output compare 8-bit register, OCR2 register, to 0. See chapter 17.7.4 of the datasheet. We start an infinite loop because the logic is implemented in the interrupt handlers. The interrupt function does nothing else but starts a counter that counts to 10. If this is done, we clear, set to 0, the counter, and start the AD conversion with the ADC start function. This function writes the ADSC bit of the ADCSRA control register to 1, which starts the conversion. When the conversion is completed, another interrupt function, namely ISR, is called, which copies the top 8 bits of the conversion result into the PWM timer register, which already directly modifies the duty cycle of the output signal. Observe the operation of the ADC SRA and ADC registers within the AD converter in the I/O view, with a breakpoint placed next to the commands of ADC enable and ADC start functions. Put a breakpoint in front of the line where OCR2 is set in the main function and in the interrupt function. In I/O view, observe the operation of the OCR2 register within the timer counter 2, and also look at our output LED. Turn the potentiometer and observe the change again. When running the program, we can observe with the naked eye that with a higher duty cycle, meaning that the potentiometer is turned up, the LED is brighter. To practice, modify the task by changing the timer 2 prescaler to 1024. Notice how much the output changes. At this time, the LED will blink if the duty cycle is reduced.
This brings us to the end of the last video in chapter 22.
Before we say goodbye, I would like to show you this RGB LED dimmer made by my colleague Bence Bárány while he was in high school. The central component is an Atmega 328 microcontroller, which is not much different from the Atmega 16 we use. It is related to today's material in that it has PWM-based LED dimming. This device can be used to control 12-volt LED strips. There are 3 LEDs in a small case, one red, one green, and one blue. Their anodes have a shared output, but all 3 have their cathodes out, so each color can be operated separately. If you control the brightness of the 3 primary colors with a PWM signal, you can mix several colors from them. The circuit is controlled by radio remote control, which is a small controller built into the panel. Of course, it can be used to control long LED strips, but the output of the microcontroller wouldn't be able to power it, so the LEDs are driven by an N-channel MOSFET. Here you can see the 3 MOSFETs needed to drive the 3 channels and the 3 different colored LEDs.
Thank you for showing us this device. If you are also interested in the written version of the curriculum, you can download the PDF format from crystalclearelectronics.au or crystalclearelectronics.hu. You can also find our Android and iOS apps under the same name. Follow us on Facebook. See you in the next video. Bye bye.
Bye!